Good to go? All right. How's it going, everyone? My name's Jimmy. We're going to talk about automated Dylib hijacking, specifically with dynamic libraries on macOS. A couple of quick notes before I get started. This was all done as sort of just a... Can't hear? Yeah, good. Sort of a pet project of mine. I happen to have a need for... Better? Good? More? Higher? Yell? Got it. All right. I had a need to do some dynamic library hijacking for some of the research I was doing. So I wound up using a lot of Patrick Wardle and Jonathan Levin's previous works. That being said, there's almost no new content in this talk compared to what they've released prior. This is just how I wound up using their research and a little bit of what I did with it. Since this is a sort of shortened time slot, I'm going to be talking really fast and sacrificing a bunch of technical details for the sake of conceptual clarity. So if you notice something wrong, it's probably intentional. You can yell at me later. I probably won't care. But notice that the resources at the end of the talk will point you in the right direction for that. A little bit about me. I'm a security research Hannibal. These are my dogs. That's my cat. He's the favorite. None of that's important. So for those that aren't familiar with dynamic libraries, I'm going to give a quick overview. I know we have some IT folks rather than developers in here, so I'll give just a quick conceptual overview of that, talk about hijacking them in general, and then talk about how I wound up automating the process. So dynamic libraries, for macOS specifically, it's important to know the macOS application structure. I won't really touch on it too much in this talk, but if you go to actually implement any of this on your own, this will become important. Really, all you need to know is that all macOS applications are special bundles. All that means is it's a directory with a very specific structure. So you'll have a contents folder, all of your frameworks somewhere, resources, and then there's going to be a special directory for macOS where all of your actual applications are launched from. Dynamic libraries, for those that are aware, also known as shared libraries, shared objects. All they are external resources that are loaded at runtime. Nothing else fancy. macOS inherits BSD style format. You'll typically see these implemented as frameworks, which are themselves special bundles that the operating system knows to traverse that special structure and load things properly. To load a dynamic library on macOS, it's all handled by a special daemon called DYLD. All you need if you want to load a library, first off, has to exist. You got to have some search paths to find it, and you need some load commands. All of these are added at compile time, and you can use certain tools such as OTool or NM or any other variety of those to actually parse them and grab out these load commands. The actual hijacking process. I'm going to start with a brief introduction of DLL hijacking just because this is a dead horse that's been beaten over and over. People already understand it. Not going to read off the slide here, but more or less, when Windows launches an executable, if an external resource is needed, it'll go through all of the search paths in order. If it doesn't exist in the first, it'll check the second. If it doesn't exist in the second, it'll check the third, so on and so forth. The way you can actually hijack these is if you find a gap in that search path, you can put your library first in the search path so it's loaded instead of the desired one. For macOS, exactly the same process, except you can do it a little bit easier by parsing these load commands. So anytime you see these lc load dylib commands or lc load weak dylib or any of the other load functions, it's going to go down and find special rpath commands that specify what all the relative paths are. One thing I want to touch on here, I'm going to mention rpath a lot. If you're from a more Unixy background, rpath does mean something special in a different context. Here, when I say it, more or less all I'm referring to is a special, relative to the current directory path. There are special things called executable path and loader path. Not necessarily important for this talk, but you will see them pop up in a couple of my slides. Vulnerable functions. Vulnerable in this context is sort of misleading because when people see vulnerable, they typically think, oh, flaw that needs to be fixed. We're not really there's nothing inherently wrong with the functionality we're abusing because it's intended. So keep that in mind, because there's a lot of ways you can use this technique for good rather than just abusing an application. The two commands that we'll look at are lc load dylib and lc load weak dylib. They both iterate over all of the RPaths, and you can search in order. The distinction between the two is the first one, if it doesn't find a library, it throws an exception and the application will exit. The second, if the library doesn't exist, it doesn't care. The execution will continue. So quick note on that. Sometimes, whether for backwards compatibility or functionality that doesn't exist without paid extensions or whatever, you'll see developers use load weak dylib instead, which, there's the typo on the slide, basically allows you to use this extra functionality, not necessarily a problem if the library doesn't exist. The important thing to note is if it doesn't exist and it's not necessarily a dynamic RPath that's being searched, you can still put your own in and it will be loaded. Now for the actual lc load dylib, if you can see at the top of the little screenshot there, it says load command 43, 44, 45, so on down. All of these are run in order by DYLD as the application is launched. So when it looks for this lib swift xpc dylib, it's going to check that first /user/lib/swift directory first. If it doesn't exist, it'll check the next one. So if there are any gaps in this path, you can abuse that and put it in an earlier path. An example application I wrote for this, just for clarity's sake, we've got tiny example, that's the binary that we're going to target. We've got dylib to hijack, and then we've got an empty nested folder /frameworks. The application's very simple. It has an external call to a print message function, and it calls it a few times. The library that we're going to hijack just defines this. It's just a wrapper for printf, just for simplicity. And then from this example application, we can see it loads this dylib, and it loads it from rpath/dylib to hijack. If you look in the second screenshot on this slide, you've got the first one checking that nested folder, which we know it doesn't exist in, and the second path checking the first frameworks folder that we know it does exist in. So we take a look at that. We know that this is a vulnerable hijack point. So if we put a rogue library in this path, ours will be loaded instead of the real one. I'll talk about how we actually do that here in just a second. I'll get back to that. So automating the process, some of this is the only original part of this talk. It's pretty simple, mostly because macOS has all of the tools you need to actually do this built in. You just have to script it. So the 3 steps you follow: scan for hijack points. Since we just did that manually and it's obvious that it's pretty easy to parse, that's a pretty simple step. You create your new library, which is as complicated as you want it to be. We'll talk about that here in a second. And then you just drop your new library and move on with life. To scan for these, as we did manually a second ago, we'll search a given directory for any binary that happens to have lc load dylib commands. So if you're loading a dynamic library, you'll then parse all of the RPaths and check those paths to see if your library exists. If it exists in the first path that's searched, just move on. If it exists in the second path that's searched, well, you know you have a gap in that, so you'll just flag it and report back, and you'll drop a library in there later. Now, wrapping and proxying functions, this is where you're going to actually do the hijacking. There are 2 ways that I've used to do it. There's the easy way and the annoying way. I'll talk about the easy way first, and that's going to abuse the built-in C attribute constructor. So to do this, this is all the source code for our rogue library. All it does is have this attribute constructor, specifies a function name, which doesn't matter, and loads and runs whatever code we want in there. So what's important to note here is as soon as the application launches and loads this library, this code is run. What's also important to note is if we didn't do this re-export here that I'm going to talk about, we would get a symbol error or symbol not found error as soon as the application tries to load try to call functions that are expected in the real library. So we'll want to add at compile time a special attribute called lc re-export Dylib that will basically grab the desired library, which you can change without recompiling, and load it so that all the symbols are found. So under normal execution, this is what the application does. Pretty simple. After we've dropped our library and the hijack point, it'll run our hijack code, and then it'll run normal execution. This would crash if we didn't actually re-export the original library. So that's the really easy method to do. You can have a single binary that's very portable and just kind of toss it around and change paths as you need with a tool called install name tool. Now the annoying way is if you want to actually examine the functionality of the library that's being imported. The reason it's annoying is because you have to have access to some sort of compiler when you're trying to automate this process. Luckily, since I'm just a developer and researcher, I can use GCC installed in my system and it doesn't matter. If you were a malware author or someone on a red team trying to actually automate this process, you'd have to package some sort of compiler with your code and then ship that off to actually do the scanning. If you want to inspect publicly exported symbols or functions that are accessible within the library normally, this next bit isn't very important, but if you want to also inspect private functions of these libraries, you'll want to use some sort of symbol phishing library. The reason I have an asterisk there, it's a term I love, no idea where it came from, never seen anyone else use it except for like one blog post. If anyone knows who came up with it, please let me know. And then you'll want to create stubs for each of the exported symbols or private symbols in the library that you want. The trick here is typically if you want to overwrite a function, you'll need to know its actual prototype. There's a little tricky way I'm using the calling convention in macOS to get around that. Not going to go too far in, but Jonathan Levin has put out a lot of research and material. There are a few other libraries around that allow you to use the core symbolication framework, which is private by Apple, but it's been very heavily reversed. You can use that to actually pull in all the privately exported symbols. The next 3 or 4 slides are all from the same source code file. This is my actual little hijacker library. All of this is just setting up the storage. So symbols are going to be all of the symbols that I'm importing and going to re-export so that we don't get any symbol errors. And then register storage. Since I mentioned we're going to abuse the calling convention, we need somewhere to store current register values before I actually get into it. And then the library hijack, that library full is going to be replaced with our desired library when this is dropped. The payload function, all I'm going to do here is keep it simple. Just print that I hijacked a function, then print the function that I hijacked. The hijack function, all it does is open the desired library, grab all the symbols from it, store those in that symbols variable from earlier, and then return. Proxy, this is where kind of the meat happens. We'll run our payload. Well, first we'll hijack, we'll run our payload, and then we'll grab the real symbol and then make a call to that. So what I mentioned before, since macOS uses the systemd ABI calling convention, it has a very specific set of registers that are used to pass parameters until it runs out of these registers, and then it just uses the stack. Well, there are special built-in standard libraries in C that allow you to use a variable number of parameters. That library, fortunately, has a lot of extra protections for the stack, so I don't have to worry about messing with that. All I have to do is care about the registers that are there. So if I just store these register values manually with a little bit of assembly, and then put them back where they belong after I run my payload, the application is none the wiser. So I don't actually have to reverse engineer the library, and I can run my code without needing to actually take the time to do that. So this function stub, I just export this or specify the symbol that I've pre-parsed from the nm utility, and then preserve the registers and call my proxy function. That's all you need to do. And once you do that, you can get this kind of output. So every time any function is called in the binary, we get a little output that, hey, I've hijacked this function, and then it'll give you the real output. If you're using the constructor method, which you probably will be if you're looking for any sort of persistence or privilege escalation, you don't need to do anything special. You can use your precompiled binary and just use the install name tool to change the paths every time you find a new library you want to hijack. If you're doing it the more annoying way, you'll just need to do a little extra groundwork to parse some of the output from some special tools, and then like build and then compile and then drop. Fancy flowchart, just kind of talking about the tool I've made. I think I'm moving fast enough. I'm not going to talk about this too much, but it's a good resource for anyone that wants to look this talk up later. Go through some final thoughts here. If you run into any issues with this, the most common one I've run into is a version mismatch issue. It's basically stating that I've tried to load a version of a library that the application isn't expecting. You can look this up in the output. It's just shows min version, max version, change yours to what's accepted, and you're good to go. You might run into some permissions issues. The scanner I wrote doesn't take any of these into account. So if you're trying to hijack something that requires elevated privilege to write to that directory, it's going to fail on you. And then my little assembly thing is hacky at best. It works on my machine. It may not work on yours. So keep in mind that more often than not, if it goes wrong, you're probably trying to do a little bit too much. Anything I've done where it's failed, I'm the one at fault, not necessarily the method. It's usually because I'm trying to mess with the stack in ways that are screwing up things downstream. But it's probably better to take a more targeted approach at that point. Use cases, I use this quite a bit just to replace actual libraries and monitor execution flow. It's a lot easier than getting dtrace or LLDB scripts set up. So it's fun just to kind of delete the desired library, replace it with my hijacker, and then watch the output in syslog. It's a great persistence mechanism. The caveat there is you have to pick something that's going to be used regularly for your code to be run. And then the biggest deal from a security perspective is privilege escalation. If you find a library that can be hijacked and it happens to run as root, but you can write to those directories as a normal user, you now have privilege escalation to root. Mitigations, there's not really anything good you can do other than proper permissioning and IT and dev rules. More or less just kind of clean up after yourself. If you have code that you're not really using anymore, just get rid of it. If you're having paths that you're not actually using, take them out of your RPath listing. That's pretty much it. Like I mentioned, I owe a lot of credit to Patrick Wardle and Jonathan Levin for all the research I've done. So I highly suggest giving them a shout out. I see a couple of people taking pictures, so I'll wait a second. All right. And I kind of blitzed through that a lot faster. Go ahead.
You know of malware? That's,
Not by name, but I have seen it. Any other questions? Cool. Well, thank you very much.